I've made quite a few videos about particle accelerators and why we use the ones that we do. But there is one thing that I haven't mentioned, and it's really pretty cool. And that is just exactly how we accelerate particles. And if you make it to the end, I'll let you know why physicists are at least as cool as surfers. I've talked about how we make electric fields to push electrically charged particles around, and that's right to a degree. In the simplest case, we could take two metal plates and connect them to a battery. That creates an electric field between the plates. That electric field can then push an object that carries an electric charge. But that simplified picture isn't how we really do it. It turns out that the electric field in most high-energy particle accelerators isn't static like that. In fact, the electric field in a particle accelerator is actually oscillating. It starts out as zero, then pushes a charged particle in one direction, then pushes it in the opposite direction. The pattern repeats itself over and over and over again. So why do we do it that way, and what consequences are there for that choice? Well, why we do that is perhaps the easiest thing to explain. It's just hard to make very strong static electric fields without a spark occurring. It can be done, but there's an easier way, and it turns out to be pretty cool. Instead, we shoot radio waves into a volume in our accelerator. We call that volume a cavity, and its exact shape and size are very important. We'll get back to that in a minute. Now, you may recall that radio waves are just oscillating electromagnetic fields. Focusing only on the electric side, we get an electric field that gets bigger, then smaller, and then reverses itself. So that doesn't sound so amazing. What's the cool part? Well, it turns out that there is a very interesting phenomenon called resonance, which we can demonstrate using an ordinary swing. You've done this as a child. You sit on the swing and you move your feet back and forth as you lean at the same time. If you do that, you eventually find yourself swinging in big arcs. What you know from that experience, but maybe never really thought about, is that there's a particular rate at which you have to rock back and forth to get the swing moving a lot. Rock back and forth too quickly or too slowly, and you don't get the full swing experience. The particular frequency at which you have to rock is called the resonant frequency. Little motions at that frequency build up over time. Particle accelerators also have a resonant frequency. If you shoot in radio waves of all frequencies into the accelerator, only a certain frequency will grow. And which frequency is the resonant one depends on the shape of the cavity in your accelerator. Some cavities prefer higher frequencies and some prefer lower ones. To get an idea of how that works, think about what happens when you blow the air out of your lungs. It just sounds like the wind. But blow across the top of a 2-liter soda bottle and you get a characteristic tone. Blow across the top of a smaller soda bottle and you get a higher tone. The soda bottle stands in for the accelerator cavity, and you can see how different sized cavities prefer different tones, which means different frequencies. And that characteristic resonant tone of a cavity allows us to put in a relatively small amount of energy in the form of radio waves, but that energy will get amplified into very strong electric fields because of the effect of the resonant cavity. By the way, the technical name for those resonant cavities is an RF cavity. That's because the cavity selects a particular radio frequency, or RF. So that's how we make electric fields in an accelerator.
Convective storms hold an extraordinary surprise. Under just the right conditions, they fire off some of the highest energy light naturally found on Earth, terrestrial gamma-ray flashes, or TGFs. Rising and falling snow and ice particles repeatedly collide, filling the cloud with electrical charge. Once the electric field is strong enough, a current flows and a lightning flash occurs. The flash produces an abrupt reconfiguration of the electric field. In some cases, a surge of electrons rushes toward the upper part of the storm at speeds nearly as fast as light. When deflected by air molecules, these accelerated electrons give off gamma rays, producing a TGF.
Very rarely, one of these gamma-ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays.